In this video, we will plot a sinusoidal waveform using the equation a sin omega t. And we will then convert that sinusoidal waveform which we plotted in time domain to frequency domain using the F50 command in MATLAB. Task 4 says plot a sinusoidal waveform in time domain with a frequency of 10 Hz with an amplitude of 10 at a sampling frequency of 1000 Hz. And we have to use a time duration of the signal 5 seconds minus 1 sample. And we need to confirm this frequency which we obtained in time domain using a frequency domain plot, and this is where we will be using the fast Fourier transform command to convert from time domain to frequency domain. And we have the equation a sin omega t. The grid of the graphs must be visible and axis should be labeled and the title should be present. I will jump into MATLAB, and in my working directory I will create a new script called task 4. After creating this, I will say clear all, and then we need to define the signal and the specifications of the signal. Now here is where things get a little different from what we did in previous tasks, because we don't have the exact time period, we don't have the starting time, finishing time defined like we had in previous tasks. Instead, we have to do it in a different approach, right? So we have the sampling time, so I will first define the sampling time using the variable fs, and I will comment throughout this video in many commands so that this will be clear for you. After entering the sampling frequency, we can actually compute the sampling period using f equals 1 over t. So here I will say ts equals 1 over fs, and this is our and after defining the sampling period, then we can define the time duration of the signal, where our starting time is 0, then sampling period is ts, and the finishing time is 5 minus the sampling period. So this one I will call it simple t, 0 to ts to 5 minus ts. This will be the duration of the signal. And two more things we need to specify: the amplitude of the signal and the frequency of the signal. So that I will label it as A and F. After defining all these parameters, then we can use the equation y equals a sin omega t. Now here we don't have omega in the parameters that we define. Omega in this equation stands for the angular frequency, which can be written in 2 pi f as well. So omega is equal to 2 pi f. So here I can rewrite this equation as a sin 2 times pi times f times t. So this is the equation that we will use. Now I will say my dependent variable y equals a for amplitude sin, inside brackets I have 2 times pi times f for frequency times t, which I have defined earlier. And after defining the dependent variable, which is y, then I can plot the time domain of this signal. So I can say plot my independent variable is t and my dependent variable is y. And after that I will just run this code, and then we will determine the necessary x and y axis limits. So this is what I obtained, and this is a sinusoidal signal, but it is very hard to interpret it because everything is closer together. So if I limit the x-axis from 0 to 0.5 as well as y-axis from like minus 15 to plus 15, I could get a better representation. So I will do all those things. Xlim, and I will have the labels and the title and the grid as well. Now I can run this and I will obtain the desired graph, which is defined for x and y axis limits, and this is a very good representation. Now this concludes one section of the uh, tasks, right? Plotting the time domain. Next, we need to plot this frequency of 10 hertz. So convert this frequency of 10 hertz to the frequency domain, where in this frequency domain graph, we should obtain a peak corresponding to 10 hertz. Now, there are many ways of achieving that, all based on the FFT command in MATLAB. And these different methods actually produces graphs of slightly different nature, but all gets the job done. So after a lot of trial and error, I have figured out a series of commands which will give a reasonable response for the frequency domain. So you can follow this, and also you can modify it as you go by referring to other sources. And this one, since we are going to another section, I will actually have a section break in MATLAB. I will take use of that so that I can just focus on the frequency domain as well. So I will start by defining the length or calculating the length of the signal y. The command is length. After that, I need to convert this length into powers of 2, and that is a requirement in this series of commands that I'm using. So to convert it to powers of 2, I can just directly use the command 2 to the power next pow 2n. So this is a command that I can use to convert the length, or take the length of the signal and then convert that length into powers of 2. After this, I can directly compute the fast Fourier transform using the command F50. So I will say capital F50 equals, the command is actually simple F50, and I need to compute the fast Fourier transform of the signal y. This is our main signal a sin omega t, and the length of the signal in powers of 2. So capital NN. So this will be the FFT of the signal y. This is not the end, because we need to do some slight modifications or slight alterations in order to properly plot the frequency domain, because this doesn't plot the frequency domain. That is very useful for us, because there are some unwanted parts as well, and the interpretation could be different. So first things first, we need to remove the mirror image, because when you directly plot the FFT, it plots a mirror image. That means the two signals on either side. But we don't need that. We only need the signal from one side. So we need to remove the mirror image. So that I will have a new variable called ffts, and then I will take the FFT, which is my fast Fourier transform signal, and then I will say limit it from 1 to the length n over 2. This will actually remove the mirror image. After removing the mirror image, I need to normalize the x-axis. Now, we compute the FFD for our dependent variable y. However, we need to actually do something called the normalization of the x-axis so that we can get the accurate frequency values in the x-axis. Otherwise, we might get some different interpretations of that. Not wrong values, but different interpretations of the x-axis. So that I will have a variable called fft, and here I will take my sampling frequency fs and multiply that by 0 to nn divided by 2 minus 1, and this will be divided by nn. So fs, so fs times 0 to nn divided by 2 minus 1 divided by nn. So this code is actually used to normalize the x-axis. After this, I can because in this task it says only compute the magnitude, right? So when you plot the uh, FFT, it's the imaginary form. So from that we need to only extract the magnitude, and that we can do it from the normal way that we compute the magnitude, which is by obtaining the absolute. I will say magnitude of FFTS is equal. We can use the direct absolute command of ff absolute command of fft. So this will only obtain the magnitude. After obtaining the magnitude, after obtaining the normalized x-axis, we can then plot the graph using the normalize x-axis as the independent variable and magnitude of the fast Fourier transform as the dependent variable. So since I need this in a different plot, I will say figure plot x fft, which is the normalized x-axis, and the magnitude. I will just directly plot this. I will only run this section. Okay, so this is my frequency domain. As you can see, there is only one single peak, and this peak will correspond to 10 hertz. So I will actually do some adjustments, like I will limit the x-axis and y-axis. So x-axis I will limit from like 0 to 50 hertz, and y-axis I will limit from 0 to maybe 2.7 into 10 to the power 4. And I will label the x-axis and y-axis and the title. And in this one, since we are plotting the frequency domain, the x-axis will be frequency in hertz. and I will enable the grid as well. Then I will run this section and see what I will obtain. And this is the interpretation of our sinusoidal waveform A sine omega t in frequency domain, and this is the peak, and if I click on top of this peak I will get the x value as 10, and our x axis correspond to the frequency in hertz. That means this sinusoidal signal that we plotted has a frequency of 10 hertz, and this is our task 2. Task 4, and this is how you can actually complete it, but I will use a specific command that we used earlier in the previous task to save these two images as high resolution PNG files. So I will say print GCF. This will be time domain.png. This one I will copy for the frequency domain as well, and I will say this is frequency domain, and then I will run this full code and I obtain the time domain plot, and this is the corresponding frequency domain plot. And I will actually open this in the Explorer, so I can open the time domain plot and the frequency domain plot and get it side by side, and this is the complete result of task 4. Next, we will actually move into controls in using MATLAB, where we will try to plot the step response of a transfer function in an RC circuit.